Hello everyone, welcome to lecture 22 on Mechanics and Materials 1. In this lecture we want to talk about the topic combined loading. We cover section 8.2 of chapter 8 of the Hibbeler book. So in this lecture we pick up where we left off in the last lecture and we start exactly with this slide. In other words, in this lecture, there is nothing new that I want to teach. There is not a new topic that we want to cover. We already learned about the four types of problems that we had: axial loading, torsion, bending, and transverse shear. And what we want to do today is to look at a combination of these. Before that, I would like to categorize them again. So an axial loading problem is shown here in the figure. You would have a normal force P, and for this type of problem, stress would be P over A. Delta, the change of length of the beam, would be PL over EA. As we will see, we would be more interested in the stress distribution in this lecture, not exactly or not necessarily in deformations. Then when we talk about a torsion problem, the stress is now a shear stress in contrast to the normal stress that was relevant for axial loading. And that stress is distributed according to the formula TR over J. Again, the angle of twist here, phi, is TL over GJ, but you know that already. So they are similar in terms of the deformation. Both problems of torsion and axial loading are similar in terms of deformation. Now, when we look at a bending problem, again, you can think of a measure of deformation, theta, which would have a similar form. But more interestingly, we are interested in the distribution of the stress here. And then you can see again, although you apply a moment, which is similar to torsion, the stress itself is a normal stress, which is similar to an axial loading problem. And the flexure formula gives us the stress distribution, which is sigma equals minus my divided by I. And then again, you can compare these two maybe, and you can see the similarities. Basically, here you have the moment, and here you also have the moment. This is a distance, and this is a distance. And then in the denominator for torsion, you have the polar moment of inertia J. For bending, you have the moment of inertia I. Again, the minus sign is just for us to know the direction of the stress. But if you are careful, you don't have to exactly look into that minus. And finally, when we talk about the transverse shear problem, the transverse shear stress reads VQ over IT. Now, if you look at these two problems, they both have shear stress, and for these two problems, we have normal stresses. In other words, if we now have a combination of these cases and we want to look at them at the same time, it makes sense to kind of categorize them like this. And as I mentioned, we are more interested in the first column. We are interested in the stresses for design rather than the deformations. Also, you can see that a box here is missing for transverse shear. That box would naturally relate to the deflection or deformation of the beam. And we have also learned how to calculate deflection, but it doesn't exactly fit nicely into this picture. Just to be clear why we are talking about combined loading, for instance, you can imagine if you have just a simple beam with circular cross-section and you apply a moment. It's a very simple problem. You just apply a moment, but that moment vector itself, it could have three components. It has a component with respect to the z-axis. It has a component in the y direction and in x direction. Now you can see that the component mz would cause a bending with respect to z-axis. So it would be a bending problem for which you need to calculate stress. But the moment my, it causes another bending stress, which would be basically minus, or maybe in this case plus mz divided by I. So these two components together already, they give you a combined bending problem that we talked about, or a non-symmetric bending problem. And then the axial component mx, it gives you a torsion problem basically. So it will cause torsion. And then for that, you would calculate the shear stress. So if you have a problem like this, usually the question is to find or to calculate the stress state at a specific point in the beam or in the shaft. And as I mentioned previously, for that matter, we are usually interested in the yellow column here. So how do we do that? How do we calculate the stress state for a combined loading problem? It's actually not complicated if you don't get confused, if you go step by step and solve for each of these cases separately and carefully. So if you have a combined loading, the first step is to find the internal forces and moments at a desired cross section. So usually in these types of problems, you are asked to calculate the stress state at a specific point on a specific cross section. So what we need to do is to calculate the internal forces and moments. Then in the next step, you find the stresses due to those internal reactions or those internal forces and moments. So you can imagine that if your internal forces is a combination of a normal force and a tangential force, then you would have a combination of a transverse shear problem and axial loading problem. Or in the previous example, we just saw it. If you don't have exactly forces, but you have moments, but then those moments have different components, they can cause torsion and bending at the same time. So you need to find sigma and tau for each of those internal forces and moments. Finally, you need to add up the effects together. And all you have to do here is to be careful with signs. So again, if you think of, for instance, stress, you need to pay attention. Is it compressive or is it tension? So ideally, you would just assume that compressive stresses have a minus sign and tensile stresses are positive. So if you are careful with the signs, there shouldn't be any problem. But more importantly, and that's a common mistake, is that you should realize that you cannot add shear stresses to normal stresses. So only you can add normal stresses together, again, being careful with the sign. So it might look like basically a subtraction, but you can either just add normal stresses together or shear stresses together. Okay, so you never add shear and normal stress together. They are basically in different directions. And if you draw the stress state, that would be very clear why you cannot do it. So this is everything for this lecture. As I mentioned, there is nothing new that I want to teach here. But what we want to do is to learn how to solve these sort of problems through a series of examples together. So we will have a few exercises now and we will go through combined loading. The first exercise in today's lecture is similar to problem 8.2 on page 418 of the book. For the block shown in the figure, determine the stress state at points B and C. You can neglect the weight of the member itself. So you have a block and you apply a force of 300 kilonewton on the point shown here, and you are asked to calculate the stress state at points C and B. The dimensions are given in the figure. You can imagine if the force was applied exactly at the center, this would be a typical axial loading problem where you have actually compression. So the stress state would be simple. But now you can see that the force is applied off-center. So due to that off-center components, you would also introduce a moment which will cause a bending. And that would change the stress state also. Okay, so this is our problem basically. What we want to do is to go through the 3 steps that we discussed previously. The first step is to find internal forces and moments at the described cross-section or at the desired cross-section. So here you can see that cross-section that we are interested in is here. And if you want to calculate the internal forces and moments there, you can see that your internal force would be 45 kilonewton. Sorry, your internal force would be 300 kilonewton upwards, which would cancel the 300 kilonewton here. So that would cause a compression, obviously. And then you have the moment 45 kilonewton meter, which would basically keep the piece in equilibrium, because you can imagine if you think of equilibrium of moments with respect to this point, the force that you have here has a distance of 150 millimeters. So it would cause a clockwise rotation, if you want, or clockwise moment. So you would need an internal moment in the opposite direction to cancel that, which would be 300 kilonewton times 150 millimeters, and that gives you 45 kilonewton meter. All right, so this is sort of your first step. The next step is to now calculate the stress states or the stresses due to each of these components separately. So if you think of the coordinate system that we have here, x, y, z, you can think that the stress that you get due to the force 300 kilonewton, it would be a compressive stress, and it's equal. It's equal throughout the cross section. So it's the force 300 kilonewton divided by area. So this is your force 300 kilonewton, again with a minus sign so that it shows it's a compression, and area is calculated from the dimensions given, so that's 0.03. And when you use the formula P over A for stress, you calculate the stress at points B and C to be 10 megapascal and compressive stresses, so with a minus sign. So this is basically an axial loading problem. But the moment that you have now is causing another stress. It's also a normal stress, but it's a bending problem. And in order to calculate the stress for that, we use our flexure formula. Again, our flexure formula usually is something like this. But we need to be just careful with that and adjust it according to the case that we are dealing with. So previously we had this one because we wrote it with respect to a z-axis. So in that example that we had previously, y was the distance from the z-axis, and m and I, they were calculated with respect to z-axis. So here is similar to that, except that the distance with respect to z-axis, or the distance from the z-axis, is now the coordinate x, according to the coordinate system we have here. The moment of inertia with respect to z-axis is 1 over 12 bh cubed, where b is the 100 millimeter side and h is the longer side, 300 millimeters. And if you do that, you can calculate the moment of inertia Iz. The moment itself is 45 kilonewton meter, so 45 times 10 to power 3, and you can see the direction is basically counterclockwise, so positive. And then you can imagine anywhere on the right hand side of z-axis here, you would get a compressive stress. Anywhere on the left hand side, you get a tensile stress due to bending. So you would actually need the minus sign. And your stress relation would read minus 200 times x. So basically you would get a stress distribution which looks like this. It's a linear function. It goes from 0 to 30 megapascal. Compressive on the right hand side, and let's say tensile or positive on the left hand side. Okay, now if you look at the bending problem, the stresses at point B and C are plus 30 and minus 30 megapascal respectively. For the compressive loading, they were both minus 10 megapascal. So what you need to do is to just add them carefully, and you end up with 20 megapascal tensile for point B and minus 40 megapascal or 40 megapascal compressive stress for point C. Exercise 2 of this lecture is similar to problem 8.5 on page 422 of the book. Determine the state of stress at point A. On the solid rod shown in the figure, the radius of the shaft is 20 millimeters. So you have a bent rod. It's fixed at point C in the wall, and you apply a force of 2 kilonewton in the y direction. With the dimensions given on the figure, you are asked to calculate the stress state at point A. So point A is on this cross section at distance 125 millimeters from the wall, and it's here on the corner. So we approach this problem exactly as we presented before. We need to go through these 3 steps. The first thing you need to do is to find the internal forces and moments at the desired cross-section. So this is the cross-section we are interested in. On that cross-section, you need to calculate the stress state, which means stresses sigma and tau, and for that you need the forces and moments. And finally, you add up all these effects together. So you can imagine, if you want to calculate the stress state on this cross section, what you need to do is to use the method of sections, as we learned at the beginning of the semester. So basically you cut the rod at that section and you write the internal forces and moments. So if you look at this piece now, you can clearly imagine, in order to keep this in equilibrium, because you apply a force of 2 kilonewton in the y direction, you would need the same force in the opposite direction. So that gives you a normal force on that cross section. But then these two forces, they cause a moment of 400 Newton meter. So in order to have equilibrium again, you would need a moment which is in the opposite direction. All right, so you can calculate the normal force and moment at the cross section. This is our first step. Now what we want to do next is to calculate the stress state on that cross section, and for doing that we would split the internal loading into a moment and a force. So the force would cause a axial loading problem basically, and the moment would cause a bending moment problem. In order to see the problem more clearly, we look at the cross section from the other side. So instead of thinking of the cross section that we would cut from the right part of the figure, we would actually cut it from the left part, so that we see the cross section like this. It's the same cross section, obviously, the point A is the same point, but you can imagine that the force and moment that you have now in this figure, they are the reactions of what you calculated there. So you would have a force 2 kilonewton that is opposite to what you had here, which is indeed then equal to what you actually applied. So that force corresponds to an axial loading problem, and it will result in normal stress. And then you have a bending moment. Here is downwards, so here it would be upwards. And you can imagine, if you have a bending moment like this, it would cause bending stresses or normal stresses due to bending and due to flexure formula. So we solve this problem into two steps. The first step is to just solve for the axial loading problem. In order to do that, you calculate the stress state at point A due to the force 2 kilonewton. That force itself, it will cause a tensile stress state, but that is uniform, and you can calculate the stress using the formulas sigma equals P over A, and then again P here is 2 kilonewton, and A would be the area of the cross section, and R was given in the problem, it was 20 millimeters. If you do that, you can calculate the normal stress to be 1.592 megapascal. Now on top of that, you would have the bending moment, and you can imagine that the bending moment you have here is with respect to z-axis. So this is the z-axis. So your flexure formula would be sigma equals m with respect to z-axis divided by moment of inertia with respect to z-axis, and then the distance from the z-axis. Here the distance from the z-axis is the coordinate x, and if you think of the signs, you can imagine that on this portion you would have compression, and on this portion you would have tension. Now on the portion that you have compression, x is actually negative, and on the portion you have compression, x is actually positive. Remember, this is the way x coordinate is set. So that means you do not need a minus that you would usually have here. So the sign is correct as it is, and then from that formula you can calculate again the stress state for the cross section, and for point A in particular you would have 63.66 megapascal. Pay attention that if you were, for instance, interested in a point on the other side, let's call it point A prime, then your stress would be a compressive stress, so it would have a minus sign. Whereas for the first problem, the stress at A prime at A and A, they would be equal. Okay, so now that you know the stress at point A due to bending and you know the stress at point A due to axial loading, all you have to do is to add them up to get the stress state at A due to the total load that you have on the picture. If you have that, then adding 63.66 plus 1.592 megapascal, it gives you a tensile stress, again, meaning that it's a plus 65.3 megapascal. So that is the answer to the problem. That's the stress state at point A, and it is made of two contributions. What we want to do next is to look into the same problem, except that in the next one, we want to change the external load. So instead of having a load in Y direction, we want to apply a load in Z direction and see how this problem will change by just doing that. Exercise 3 of this lecture is similar to problem 8.6 on page 423 of the book. Determine the stress state at point A of the solid rod shown in the figure. The radius of the shaft is 20 millimeters. Now, if you look at the figure, is exactly what we had in the previous exercise, in exercise 2. Except that now the direction of the force that we apply is different. Previously, we applied a force which looked like this. Now we want to know, just changing the direction of the force this much can change the stress state at A or not, and how. So what is the influence of that? And also, more importantly, you should remember that if you have a usual question, it may not be exactly this or this direction. We may have a force in a direction like this, which would have indeed two components. So you would get a mixed effect from both exercises eventually. All right, so but now let's say we have this less complicated case and we know the force is exactly vertical in the opposite direction of the z-axis. So what we do is, again, very similar to what we had done before. You need to find the internal loading at that cross section where you are interested in. So here point A is on this cross section, so we need to cut it at that cross section, calculate the internal loadings. Then from that, we calculate the stress state, sigma and tau, and then you add up the effects together. So if you cut the rod at this section where point A is on, you can see the forces and moments. So the internal force you have there, it would be 3 kilonewton upwards to cancel the downward force. So that comes from equilibrium. Then you can imagine that this force that you apply, it has a distance in x direction, which would cause a moment in y direction. Okay, so if you multiply the force itself times that distance, it would cause a moment with respect to y direction. And that means you need to have that much moment in the opposite direction to have equilibrium of moments in y direction. So that's why you get your 600, because it's basically multiplying 3000 by 0.2. So that is your my component. But also, that force has a distance along the y-axis. So if you assume that you just bring the force there, you also multiply that force by distance 0.15, and that would cause a moment now with respect to x-axis. So then you need a moment in the opposite direction to cancel that or to keep equilibrium. So that gives you 450 Newton meters moment or internal moment with respect to x-axis. Pay attention that the directions are shown here. So if you assume that the moment here in the y direction is positive, this is actually minus 600, but for the x-axis is the same. So 450 is actually positive because the force would cause a moment which would have been negative. All right, so this is our usual equilibrium. There is no complication there, but you can see that there are basically three types of internal loadings or three components. There is a shear force, there is a moment with respect to y-axis and moment with respect to x-axis. What we do next is very similar to what we have done before. Instead of talking about that part of the cross-section, which is basically on the other side, so we look from behind, we look at the opposite section to have a better representation. So that would be now your cross-section. And the forces and moments that you see here are exactly the opposite of what you see here. So they are reactions of those essentially. So here you would have a shear force downwards and then a moment that is my. So it's now plus, it's in the same direction as y-axis, and then you have mx, but now it's, let's say, in the opposite direction of the x-axis. Okay, due to these three loadings, you would get three different stresses and then you need to add them up. And that's what we want to do now. The first component that we want to talk about is the shear force itself. So if we have a shear force downwards, that means you would have a shear stress distribution on that cross section. And the question is, what is the shear stress at point A? For that, we use our transverse shear formula, VQ over IT. I is the I for the cross section, so we know that is pi over 4 c to the power 4, and c is the radius, which is 20 millimeters or otherwise 0.02 meters. So we know I. T is the thickness at A, which is 2 times the radius. Q is the moment of inertia of the cross section above the line at which we have point A. So in order to calculate Q for that cross section, we need the distance of the centroid from the neutral axis, and you can read that from the tables, or you can calculate it, but we have done this before, so we know that if you have a half circle, the centroid would be at the distance 4 times c divided by 3 pi from the center. The area is half the area of the circle, and if you multiply those, you get Q. Okay, if you insert all of these, you will have a shear stress that is 3.18 megapascal. So this is your first part. This is your transverse shear problem. The next part is to deal with the bending with respect to x-axis or in the opposite of the x-axis, it doesn't matter really. So the stress distribution according to the Fleischer formula is here, is mx, moment with respect to x-axis, times distance from the x-axis divided by moment of inertia with respect to x-axis. And then again, you would use your knowledge to judge about the sign, whether you need a minus or not. In any case, for this problem, you can see that your point A is on the neutral axis. So the stress is in fact 0 due to bending moment with respect to x-axis. But then again, if you think about the portion where z is positive, the stress would have been tensile, and below it would be compressive, so you wouldn't need a minus here. All right, so this is the second part. The third part and the remaining part is now to deal with the moment with respect to, let's say, y-axis itself, or what we would see here as the normal moment. Now, this normal moment, unlike the bending moment that we have here, it would cause a torsion, or it would cause a twist, which is essentially a torsion problem. So for a torsion problem, you remember the relation we had for the shear stress distribution was tau equals TR over J, and T was the torque, R is the distance from center, and J is polar moment of inertia. Again, polar moment of inertia for circle is pi over 2 c to the power 4, and c is the radius, which is 20 millimeters. Point A is at the outer wall. That means the radius there is c. This is the maximum radius, which is also 20 millimeters. And the torque that you have there, T itself, is my, or there is the normal moment, that is 600 Newton meters. Okay, if you insert all of that, you end up with the stress state at A, which looks like this. So you would have no normal stress, but your shear stresses are these two, and you need to add them together to get your shear stress state. All right, so this was everything we wanted to have in this lecture with regard to the topic combined loading. As I mentioned, in this lecture, there is nothing new that I want to teach or I can teach. It's, as the title suggests, it's just the combination of what we have learned so far. And the only important thing that I can emphasize on is that you need to go carefully through the 3 steps separately and make no mistakes when you add the stresses together. And also be careful with respect to signs. All right, this was our lecture on the topic combined loading. We covered section 8.2, and that was all we wanted to talk about chapter 8 of the Hibbeler book. What we want to do in the next lecture is to talk about energy methods, and that would be chapter 14 of the book. I'll catch you in the next one.